We are off to chapter 9 here, which is solutions. We talked a little bit about some of this stuff last week, I think, during discussion. So we're going to actually start in the middle of the notes, and then we're going to work our way backwards after that. So if you want to catch up there where we are in the notes, probably about middle where it talks about mass percent. So that's where we're going to pick up. And then we'll come back to front stuff and cover some of the stuff we need to cover. But I think right now we're going to kind of start midway through since we sort of talked a little bit about it, I think, last week during discussion. And then we'll come back and officially talk about the front part of it here a little bit later this week. So in this chapter, which is chapter 9, we're talking about solutions. And a reminder, as we talked about last week, I think during discussion, solutions are really those guys that get the aqueous symbol next to them. Solution is really made up of two parts. One is the solute, which is the smaller part of the solution, and the solvent, which is the larger part of the solution. So when you take both of those together, that does represent a solution, which really is a homogeneous mixture, which means everything really dissolves in one another. And for example, again, if you took water, which is a pure liquid, and you took some sodium chloride, which is a solid, you mix these together here. The sodium chlorides are solute. It will dissolve in our larger part, which is our solvent. And that would get us a sodium chloride solution that would get the aqueous symbol next to it. Something with the L symbol, which is liquid, is really just one substance by itself. There's nothing else mixed in with it. So that's why water doesn't get an aqueous symbol, but it gets a liquid symbol, as it is just water by itself. But again, if you take something like water and put something in it that dissolves, that's basically what you get for our solutions. One of the important sort of aspects of solutions is concentration. And we'll talk about some of these concentration sort of units. If something is really concentrated, it has a large amount of solute. So a high concentration has usually a large amount of solute, and a kind of lower concentration has a smaller amount of solute. Okay, so kind of picking up there midway, I think in the notes, we're going to talk about first, again, important sort of concentration unit that we might have talked about in discussion last week, but just to officially talk about it here, this is mass percent, our percent mass / mass. And that is the mass of the solute over the mass of the solution times 100%. And especially with these type of problems, as we might have touched upon, it is this bottom one that you really do need to be careful of. It is very, very common in these problems that they do give you sort of the two parts of the solution separately in terms of their values. So they'll oftentimes give you the mass of the solvent, and they'll also give you the mass of the solute kind of separate in the problems. So once again, it's really important that you take both of these and you add them together to get the actual mass of our solution here. Again, it's a very common mistake that people will just take the solvent because it's like a larger number, and they'll just divide by just the solvent. So you want to make sure that you do get both of those for the mass of the solution. This is really sort of a grams over gram type of unit. So that means is if you had a 5.5% by mass sodium chloride solution, you can really turn that into a usable sort of conversion factor by assuming 100. And what that would mean is you would have 5.5 grams of sodium chloride in 100 grams of solution. And you could use it as a conversion factor the other way as well. In 100 grams of solution, you would have 5.5 grams of sodium chloride. So sometimes you're given the percent by mass or some percent concentration unit, and you need to use it in the calculations. And a lot of times it's easier just to kind of turn it into a conversion factor and do a conversion problem. You could absolutely kind of plug and chug into this equation and solve for whatever is missing. It's the same math really, but sometimes it's easier to see it as a conversion factor when you're doing the calculation. So let's try one here. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of calcium chloride. So you're looking for okay, let's take a look at it. So again, a solution, as we were just talking about, is basically two things. It is a solute plus a solvent. The smaller one is the solute. So in this case, our calcium chloride is our solute. Yes, our calcium chloride is our solute, and 50 grams of water here would be our solvent, right? Which is our larger part of the solution here. By the way, the solute is always the name of the solution. So if you have like a potassium chloride solution, it's potassium chloride. So whatever the actual name of the solution is always the solute when you look at it. So in this case, our mass of our solute will be 2.5 grams. Our mass of our solvent, which is the larger part, will be 50 grams. That means it's important here that we actually do add them together to get the mass of the solution. And that would be 2.5 plus 50 grams, giving us 52.5 grams of solution. So to calculate our percent mass to mass, we're just going to put our numbers in. 2.5 grams divided by our 52.5 grams, which once again is the actual solution, not just the solvent here. And that's going to get us 52.5. Looks like 4.76%. And sometimes you just write M/M, and maybe calcium chloride would be the right choice there. Calcium chloride. Any questions on that calculation there? Yeah. Yeah. I won't say every situation, but I would say very common in a situation where you have to calculate something like percent mass to mass like this. It's very common in those problems that they do give you the mass of the solute and the solvent separate from each other. So it's very common in these type of problems, that specifically this calculation, that you should get them together. You won't always have to do it. They may just straight up give you the mass of the solution. But definitely if you got kind of two numbers, you want to look at it, make sure it's not the solute and the solvent. We'll see some other percent compositions here that you don't have to worry about it because they're usually volumes, but definitely in this one, mass to mass, is very common. They're separated out. Yeah. I'm sorry, say it one more time. Yeah, to calculate it, it's always the mass of the solute over the mass of the solution. So it won't always be that number, obviously, but whatever the solute its mass is divided by the mass of the solution. Other questions? Yeah. Okay. Let's try another one here. Concentrated hydrochloric acid contains 37.2% by mass HCl. What is the mass of the HCl that's in 35.5 grams? Okay, let's take a look. So again, this is percent mass to mass as well, which once again is our mass of our solute divided by the mass of the solution times 100%. So in this particular case, we are given the mass to mass percent. So we actually do have this guy given to us, which is 37.2%. We are looking for the mass of the HCl. And we have 35.5 grams as the mass of the solution. Now, I'm really looking for, if we check off, we have this, we have the mass of the solution. I am looking for the mass of the solute. If you are not sure that that is really what you're looking for, once again, the name of the solution, which is hydrochloric acid solution, and you're looking for how much hydrochloric acid it is, that is always going to be the solute. So whatever the name of the solution is the solute. So in this case, since we are looking for the HCl, that's how, again, we know it is definitely the solute in this particular case. So you have a couple of ways you can solve it. You literally could just plug and chug into that equation. You alternatively could take the percentage and kind of turn it into a conversion factor. So that's what I'm going to do. I'm going to take a more dimensional analysis approach. So that 37.2% means I have 37.2 grams of HCl in 100 grams of solution. Or I could use it as 100 grams of solution is 37.2 grams of HCl. So basically that is taking our 37.2% by mass and turning it into basically some conversion factors to use in this problem. So that's the approach I'm going to take. And that means that I know I have 35.5 grams of the solution. I want the solution to cancel, which means I do want to actually use the conversion factor like that. So that the solutions on the bottom gives me 37.2 grams of HCl and 100 grams of solution. The grams of solution here will cancel, and that will leave me how many grams of HCl, which is 35.5 times 37.2 equals divided by 100, about 13.2 grams of HCl would be dissolved in that solution. Any questions on that? Now, if you just plugged and chugged into the equation, you would have done 37.2% equals the mass of the solute divided by 35.5 grams times 100%. Math-wise, you would have done the exact same math as above. So it comes out the exact same when you solve for it. You would multiply the 35.5 to this side. You would divide by 100. And you end up basically with the same math. So however you want to do it, it's basically the same. You can plug it in, or if you want to take a more dimensional analysis approach, seeing the units might be helpful as well. Any questions on that particular one? Okay, so there's a couple other sort of percent concentrations that are also sort of important. The next one is percent volume to volume. So this is percent volume to volume. It is kind of the percentage, like, they use like an alcohol, percent by volume alcohol or something like that. This is volume over volume, which is kind of like milliliters over milliliters. So it is the volume of the solute divided by the volume of solution times 100%. Unlike the percent mass to mass, and sort of was the earlier question, in this type of percent concentration, you usually don't have to worry about the bottom one there. It's usually just given to you the volume of the solution. You don't usually have to do some adding or anything like that in most cases. So that one's usually pretty good. It works the same way. Again, if you had a 4.5% by volume sodium chloride solution, you can basically turn it into a usable conversion factor by saying 4.5 milliliters of sodium chloride in 100 milliliters of solution. Or you could use it opposite there. 100 milliliters of solution is 4.5 milliliters of sodium chloride. 4.5. So kind of like the other one, you could basically turn it into a conversion factor, or just like the other one, you could plug and chug into this equation and solve for whatever's missing. It's, again, really the same math, whichever way you're more comfortable doing. So this is really sort of volume over volume in this particular one. The last sort of percent concentration is mass to volume. So again, this one, which is mass to volume, deals with grams to milliliters, basically, in most cases. So this is sometimes referred to as percent mass to volume. That's kind of grams over milliliters. That's kind of like density, right? Grams over milliliters, kind of the same idea. And it works the same way. It is the grams of the solute over the milliliters of solution times 100%. And just like the other ones, if you had a 4.5% mass to volume sodium chloride solution, that would mean that you had 4.5 grams of sodium chloride in 100 milliliters of solution, or in 100 milliliters of solution, you got 4.5 grams of sodium chloride. So once again, you could turn any of these percent concentrations into conversion factors. Just assume 100, because frankly, it keeps the numbers the same. So that's the way we assume 100 of it. And you can turn them into conversion factors. Or again, you can plug and chug into the equations, whatever's missing, and solve for what's missing. Again, if you do each one correctly, they should come out the same because you're basically doing the same math. Any question on that one there? Let's take a look at one here. What is the mass to volume percent of Br2 in a solution prepared by dissolving 12 grams of Br2 and enough carbon tetrachloride to make 250 milliliters? Okay, so we're looking at the percent mass to volume here. So that is going to be the mass of the solute divided by the volume of solution times 100%. In this particular case, this is going to be our solute. And in this case, they did give us the volume of the solution. The solvent in this case is actually carbon tetrachloride is our solvent. Not that you necessarily need it to solve the problem here. But it is carbon tetrachloride. This is a case where water would be a really terrible solvent. And that is because Br2 is nonpolar. Yeah. And carbon tetrachloride is also nonpolar. So these two things mix really well together. Again, we might talk a little bit about it, but we will later as well. The idea of like dissolves like. So nonpolar and nonpolar things really work well together. Polar and nonpolar things, not so good. They really don't mix. So that's why, again, in this case, the solvent is carbon tetrachloride. In this case, we actually have everything we need the way we need it. We should just put it in. So 12 grams divided by 250 times 100%. And 4 point something, I think. That'd be 4.8% mass to volume, Br2 in this case. Any questions on that there? So remember when we kind of mix things together, they need to be kind of similar to each other in terms of how they interact with one another. So again, things that are polar and polar work really well together. Ionic and polar work well together. Non-polar and non-polar, like this example. And it's just that crossing over polar and non-polar things, they really don't interact really well together. Any questions on any of these percent compositions or percent concentrations, I guess that's what I said. All right, let's try one more here. Calculate the grams of KCl and the grams of water in 225 grams of an 8% mass to mass KCl solution. Let's see what you come up with here. Looking for dealing with percent mass to mass, so that's a good place to start. So we'll start with our formula here, which is our mass of our solute divided by the mass of the solution times 100%. We're looking for the grams of KCl, so that is really our solute is what we're looking for. We have 225 grams of solution, so that is the mass of the solution. It's 225 grams, and we also have the percent by mass there given to us. So once again, you can either plug into this equation or you could use the percentage as a conversion factor. If you took the conversion factor approach, again, that means that there are 8 grams of KCl in 100 grams of solution, or in 100 grams of solution, there are 8 grams of KCl. Since we do have the mass of our solution, we could kind of just set it up as a dimensional analysis problem. 225 grams of solution. We want the solution to cancel, so we'll use our guy over here, which once again is really the same math. If you plugged it into the top equation here, you'll end up with the same math that you're doing. Again, the grams of solution will cancel. That'll give us 225 times 8 divided by 100. gives us 18 grams of KCl, which is our mass of our solute. Any questions on that part of it there? The second part is we're actually looking for how much water that's here. So we do have the mass of the solution, which should be the mass of the solute plus the mass of the solvent. In this particular case, this is an ionic compound, which means the solvent is most likely going to be water, which is why they're asking about water. Water is a really good solvent for things that are ionic. So this basically means that the mass of the solution was 225 grams. The mass of the solute we just calculated, which was 18 grams, plus really the mass of the water here, which is our solvent. Basically, you're just going to subtract our 18 to the other side, and that will get us 225 minus 18. Looks like we end up with 207 grams of water. Let's see. So this solution here, this 207. So this solution here is basically made up of 207 grams of water and 18 grams of KCl. Mix it together, and you just made a 8% by mass solution, basically. Any question on either of those things there? Okay, so these percent concentrations do pop up. Probably mass to mass pops up a lot, and percent by volume pops up a lot. But really, the most common sort of unit of concentration is molarity. And molarity is big M, which is really moles of solute over liters of solution. Most people just go big M, moles per liter is usually how most people sort of think of molarity. So if we do have a 4.5 molar sodium chloride solution, what that means is you have 4.50 moles of sodium chloride per liter. And it is really highly recommended, as I might have touched upon when we were kind of going over it last week as well, to get rid of the big M and put it both units in there so you can see them, especially when you're doing calculations, because it's very, very common. People really have no clue as to where the liters is or the moles is, and they just see the M and think moles, you know. So it is two different units that are there. The number always stays with the moles, and it's always 1 liter. So that is how molarity works. Numbers, the number of moles there are, and it's always per 1 liter. And should always get rid of the big M when you're doing calculations, so that you can see everything. So molarity, which is moles per liter, is really the most common unit of concentration that you see. It's probably the units that you see on most of the bottles that you use. The bigger the M value, the more concentrated it is, and the more careful you should be. Yes. You see something with 18 molar, that's very, very strong. As opposed to if the molarity was very small, it's a little bit more diluted, not as strong. So something like point something molar, not too bad. But if you see some double digits there, even some single digits, high to single digits, it's fairly concentrated. You should think of molarity sort of as a formula, and we do sort of rearrange it a lot to solve for any of these things, molarity, moles, or liters. If you wanted to solve for liters, it would be the moles divided by the molarity. If you wanted to solve for moles, which is a very common process, that is liters times molarity. So those are sort of 3 ways to rearrange the molarity sort of formula to solve for moles or liters, which again is very commonly done in a lot of calculations. Couple of important conversions that we use a lot with molarity is 1,000 milliliters is 1 liter, because very common we measure volume in milliliters, and you need to convert it to liters or vice versa. So that conversion is used a lot. The other thing is a lot of times we're not necessarily given moles all the time, just right off the bat. So going from grams to moles is a very common way that we calculate molarity. A reminder to go from grams to moles, that is our molar mass from the periodic table that allows us to do that. So that's a very common sort of conversion that you need to do when you're trying to calculate some molarity to get it into moles. So grams to moles use a molar mass, and milliliters to liters, liters to milliliters, very common conversion. It does need to be in liters when you're using molarity. And if you're using a volume such as this, it does need to be in liters. You shouldn't multiply it by milliliters. I won't say you can't do it, but it doesn't give you moles. It gives you what's known as millimoles, and you'll be off by a factor of 1,000. So always safe, just convert the volume to liters when you're using it with molarity so that you won't be off or anything like that. So when we do have something that is 1 molar, it does mean that there's 1 mole of solute dissolved in 1 liter of solution. How sort of molarity works with ions, when we talk about something like what we see there, which is 1 molar sodium chloride, in solution, it really is sodium ions floating around and chloride ions floating around. So how molarity works is it works very much like stoichiometry. If you have 1 molar of the whole thing, it is basically a 1-to-1 relationship between those two. So the molarity of the sodium ion will also be 1 molar floating around. And it's also a 1-to-1 relationship between those two. So the molarity of just the chloride ions floating around would also be 1 molar. If you had something like a calcium chloride solution that had a concentration of 1 molar, when it breaks apart into a calcium ion and 2 chloride ions in solution, for every 1 of the whole things, you get 1 calcium ion, which means the concentration of just the calcium ions is also going to be 1 molar. But when we look at the whole thing here to our chloride, it is actually a 1-to-2 relationship. You get twice as much chloride ions floating around that solution for every 1 that you drop in there. So to get the correct concentration for the chloride, you would actually take 2 times the 1 molar. And it would actually be 2 molar, the concentration for our chloride. Again, because there's twice as much chloride in that solution, because you get 2 for 1, basically. So molarity is not additive. Obviously, 2 and 1 does not equal 1, right? But that is the relationship of how the ions that are floating in a solution, their concentration versus the whole thing together. Something like calcium chloride is a strong electrolyte, which means it will not stay together. So when it's in solution, it really is the ions floating around. So sometimes you may be asked about the individual ions, and that's how you relate the concentration of the whole thing to the individual ions. If it breaks apart into like a 1-to-3, multiply the concentration by 3. If it breaks apart a 1-to-1, it's the same. 1-to-2, multiply it by 2. Whatever the sort of stoichiometry is, how the whole thing breaks apart, is how you get to the concentration of the individual ions in that case. So let's take a look at one here and see. So what is the molarity of a solution prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters? If we go to the periodic table, potassium is 3910 and Br is 7990. All right, so calculate which is moles per liter. So the first thing you might want to look at is, do we have any of that? And we obviously do have the liters part, so that's good to go. It's not in milliliters or anything like that, so it's good to go in the right unit. We don't have the moles, but we do have the grams. So once again, that would be the periodic table is going to allow us to convert grams to moles. So this is KBR, so we really just need to add those two together, and that gives us 119 grams per mole. Would be our molar mass. So the first thing we need to do here is take our grams of KBr using the molar mass from the periodic table. We're going to convert it into moles so that we have the correct unit there up on top. So that's going to be, whoa, I'm not sure I just hit there. Maybe, there we go. 15.6 divided by 119. Going to give us 0.131 moles of KBr. Which is the top part of what we need. Now we have really everything that we need. So the molarity here would be our moles, 0.313 moles divided by 1.25 liters, going to give us 0.105. In terms of units, they don't cancel out, so you could leave the moles with a number per liter, or you can write 0.015 big M and maybe KBR at the end, so whatever you like there. Any questions on that calculation there? So again, you do need to convert it into moles, and it's still the same grams to moles sort of conversion that we talked about in the previous chapters. So those are two very common sort of calculations you have to do to get yourself to the molarity. Any questions on any part of that there? Okay. Let's try another one here. What is the mass in grams of sodium nitrate that is required to make a 2.5 liter solution that has a molarity of 0.15 molar? Some numbers that might be helpful here: sodium 2299, nitrogen 1401, and so obviously we're dealing with molarity, which is moles per liter. Now, if we pull out the information here, we obviously have the liters here as 2.5. We also have the molarity, which is 0.15 molar, and we're looking for really grams of sodium nitrate. So if you're not sure, you could kind of circle what you got. You got that, you got that. So clearly you're missing moles. So that's probably a good place to start. The moles here would equal the liters times the molarity. Once again, though, I would recommend taking your molarity and turning it into both units so you could see it. And again, that is the one way you could turn it in there. You could also, if you needed to, want to use it as a conversion factor, flip it around as well. So if we did our math here, that is going to get us 2.50 liters. And in this case, we want the liters on the bottom, the moles up on top. We're basically multiplying, obviously, by the molarity here. The liters will cancel, and that will get us 2.5 times 0.150. Gives us 0.375 moles of sodium nitrate. Any questions so far on that? Moles is good because we are looking for grams. So what's left is our conversion from moles back to grams, which again is the molar mass here from the periodic table to do so. If we add up all the parts there from the periodic table, we got a 2299 for our sodium. We got a 1401 for our nitrogen, and we got 3 times 16 there for our oxygen. So adding up all those parts there gets us 2299 plus 1401 plus 3 times 16. Looks like 85 grams per mole. And that comes from the periodic table. And we're going to use that to convert our moles into grams. So doing the same calculation we did in a previous chapter here. We want the moles to cancel. So moles are going to go on the bottom. And 85 grams of NaNO3 will go up on top. That way the moles cancel. That's going to get us times 0.375. Looks like 31.9 grams of sodium nitrate in this case. Any questions on that calculation there? So basically what this means, if you weighed out 31.9 grams of sodium nitrate, dissolved it in enough water to make 2.5 liters, mix it up really well, you would have a solution that has a molarity of 0.15 molar, basically. Yeah. Any questions on any of those steps there? Yeah. So we talked a little bit earlier or a second ago about ions and how concentration works with ions. So if we look at each of these separately, this is sodium sulfate. So when we have something like sodium sulfate, really when it is in solution, it really is no longer together because it's a strong electrolyte. And really what you have floating around in that solution is a couple of sodium ions and one sulfate ion. So basically in that solution, that's basically what you got floating around is these guys here. Again, you wouldn't have any of the sort of whole units together. And like I said, not in all cases, but sometimes you may be interested in really just the concentration of one of the ions or the other. And again, the way that we do this is very much like stoichiometry. We could look at sort of the coefficients. And again, here, this would basically be 1. So for every one of the sodium sulfates, you basically get 2 sodium ions that start floating around. And what that means is basically twice as concentrated. So the concentration of just the sodium ions in this case would be 2 times 1.2 molar, which would give you 2.4 molar. So if you had a question where you were interested in just the sodium ions concentration or something like that, that would actually be the starting concentration you would use because, again, you get basically a 2-for-1 situation there. Question on that there. For our sodium sulfate, it is a 1-to-1 relationship, which means the concentration of the sulfate would be 1 times 1.2 molar, and that would get us 1.2 molar. So that is the sort of quick calculation of how you get to the concentration of the ions, just to show you the long version of it and how it gets there. Is if I start with the right number, that would probably be better, I suppose. Let's start again. There we go. So if we started with our original guy here, 1.20 moles of sodium sulfate per liter, which is basically what molarity means. We could do a stoichiometry relationship here. Again, that is a 1 mole, just like we did stoichiometry, of sodium sulfate gives me 2 moles of sodium ions. So we could do that little calculation there where 1 mole of the whole thing gives you 2 moles of the sodium ions. Moles of the whole thing cancel, and we end up with 2.4 moles per liter of just the sodium ions. Hence the multiply by 2 part. That's basically the shorthand for not doing the stoichiometry part of it. It's the same thing here for the sulfate. If you look at sulfate, 1.2 moles of sodium sulfate per liter. It is from the equation a 1 mole to 1 mole relationship, just like we talked about with stoichiometry. And if you did the long calculation, this would be 1 mole of the whole thing, gives you 1 mole of sulfate. Moles of the whole thing cancel, basically multiplying by 1, and that gives you 1.2 moles per liter of sulfate. So this is sort of the longer version of multiply by 2 or multiply by 1. So in a calculation, you could just quickly multiply by the coefficient, and it's a quick way to get to the concentration of just the ions. Once again, they're not additive. Again, if you add this number and this number, you obviously don't get 1.2, but it is sort of the proportion in terms of the concentration that's there in the actual solution. As you see from my really bad picture here, there's basically twice as much sodium ions as there is sulfate. So the concentration of the sodium ions is twice as much as what you would have for the sulfate ions. Question on that one there. All right. So we would do the same thing for this guy here. And that obviously breaks apart into 2 potassiums and 1 chromate. And we could get the ions by basically doing kind of the same calculation. Any questions on that there? All right, we will lay it up there for today.